So welcome everybody this afternoon. In our very special colloquium, we have a very special guest today. It's Professor Ewine van Dishoeck from Leiden University, but she has also an affiliation at the Max Planck Institute in Garching. She started her career as a kind of native chemist in Leiden, so she started studying chemistry really. But then, and I have that from, so yes, she has a wiki page. A little anecdote, namely that her supervisor at that point actually passed away and she had to look for some solution. And so she turned into astrochemistry, or rather say molecular astronomy, which later turned into astrochemistry. And so she did her PhD in 1984. Entitled Photodissociation and Excitation of Interstellar Molecules, supervised by Harm Herbing and Alex Delgado. Now, since then, her career was shooting up very quickly, and she was part of basically all the infrared missions we had ever since. So she started with ISO, then Spitzer, Herschel, ALMA, and then last but not least, JWST. And in each case, she was involved groups that have actually access to the early data. And that was very fruitful, I would say, extremely successful collaboration also with ESRON, which is the analog to this institute, so the Space Research Institute in the Netherlands. So she was giving the science background and told them what to do and what kind of instruments are useful. And then on the other hand, she could promote that with her international standing. She got numerous prizes for her career and awards. The wiki page lists 9 of them. I only mentioned the last 2. So in 2022, she got the Zwicky Prize for Astrophysics and Cosmology. And in 2018, the very prestigious Kavli Prize for Astrophysics. And I cite here, for her combined contributions to observational, theoretical, and laboratory astrochemistry, elucidating the life cycle of interstellar clouds and the formation of stars and planets. Now, what I found maybe most impressive is actually the number of PhD students she has supervised. So we talked about this, it's about 50 in her career. And you will actually, when you go around this world, visit any institute that does star and planet formation, you will rarely find an institute where there's not a single person, at least, who was actually educated by Ewine. So I think in this way, her views of things will live on, certainly among the next generations of astrophysicists. And to say that, our institute is not the next exception, because we have Mr. van Tilwiske, who was supervised by. Take it away.
All right. Thank you very much, Peter, for this warm welcome. I've been here only for slightly less than 24 hours, but I've enjoyed myself very much here in Graz. It's always an institute that I wanted to visit ever since you and Christiana moved here. And I'm really happy to see how a lively institute is over here, going into many directions that are very topical now, both in terms of space physics, but also in terms of exoplanets and how we make them. So today I'm going to take you on a tour, a rather broad tour of the regions in space where new stars and planets are being formed. And I'll do that both at a rather global level for those that are not so much an expert in this area, but also there are a few places where I'll go a little bit deeper for the experts in the audience. What are we trying to do? Actually, the overarching goal of the research is to follow the trail of molecules all the way from the dark clouds in which they are formed, the dark clouds that we see there on that first picture, to the protostellar stage. Now we have zoomed in already considerably to the disk stage. We zoom in further, and the planet-forming disk out of which both planets and comets can be formed. The kind of questions that we ask is, We know that there is lots of dust grains in these clouds, and these dust grains can have ice around them. And one of the questions is, is this ice preserved by the time we get to a disk and maybe to a comet? So we're trying to figure out what is the chemical composition at each of these stages. Is it inherited? Is it going straight from there to there? Or is it reset along its route from the dark cloud to the disk? And I know there's a lot of people interested in exoplanets, and of course, what of all of this then sets the composition of the exoplanets. We know we have a low carbon over oxygen ratio here in the starting point, but there are planets that have maybe carbon over oxygen much larger than unity. How do you get there? What kind of sets that? And what is the role of the disk, and especially those planet-forming disk, in making all of this happen? All right, good. So we've done all of these studies with previous telescopes, but now, of course, we have the new kid on the block, and it's JWST. And so that is what I'm going to focus on. But all of this is multi-wavelength studies, and certainly ALMA comes in very much as well. What are the instruments? We have both spectrometers and cameras on Webb. And of course, most of our research is done with spectrometers. And I've been part of the MIRI, the mid-infrared instrument, that is built by a consortium of European institutes together with the US, and the Netherlands has been heavily involved in this. And this is indeed one of those instruments that was not part of the original plan of JWST, but that we had to argue as scientists that it was really important to have the mid-MIRI instrument. Now, of course, it's the second most popular instrument on Webb after NearSpec. Spectrometers take up more than 70% of the time of Webb. Imaging makes all the beautiful pictures, but most of the science actually comes from the spectrometers. So my involvement goes back to the late 1990s, and I'm very happy to see it launched in 2021. Here you see the packaging of MIRI together with the other instruments that is really behind the telescope. And what is special is that we cover basically the 1 to 28 micron range at a resolving power of about 3000. And at the sensitivity, of course, that is a factor of 100 to 1000 better than earlier instruments. So there's a huge discovery space actually with JWST. Now, in return for building the instrument, we also got some guaranteed time with the European consortium, and we decided to put that in a number of rather large programs that I will talk about here. One of them is the embedded state of star formation, when you're still building up the stars, the so-called protostars. That's the JWST program that I am actually leading. That was sort of a medium size, some 50 hours of JWST time. And then there's the protoplanetary disk, the MINDS team, led by Thomas Henning and Inge Kamp, of which my group is also a part, which is a 120-hour program that looks at 50 disks across stellar mass and age. Then there are also a number of early programs in cycle 1 that are very related to this, that I will also cite from a little bit. But first, I want to thank everybody, especially my students, postdocs, colleagues, everybody on the Joins and the MINDS team for making this possible. Indeed, you talked a little bit about the scientific family, and it's very good to see sort of both the scientific children, but also the grandchildren doing very well in all of this science that you see here, together also with actually some of our US colleagues. Okay, so if you're an astrochemist and you ask, why should I use JWST? Why can't I do everything that we need to do with ALMA, for example? ALMA is a fantastic machine for astrochemistry, the telescopes in Chile. Well, that's very good actually for doing rotation spectroscopy. But with JWST, we're actually looking at the vibrational modes, the stretching modes and the bending mode. And whereas ALMA has incredible sensitivity to complex molecules at very low abundances. So this technique is incredibly sensitive. You can see abundances of molecules down to 10⁻12 with respect to hydrogen at a very high resolving power of 10 to the 7. It cannot do everything. In particular, it cannot see molecules that do not have a permanent dipole moment. So any symmetric molecule, think of C2H2, think of CH4, think of CO2, that is impossible to see with ALMA. Moreover, ALMA cannot see solid state molecules. So a molecule, when it is in a solid state, it can no longer freely rotate. Of these polycyclic aromatic hydrocarbons, that is what we can actually detect with JWST. So the two techniques are still very complementary in what they are doing. Oh, okay.
Ach, jetzt op toch.
I think. All right.
It comes back automatically. Share one.
Oh, I need to reshare, give it again.
It's coming, it's coming.
Remember where I was?
Maybe not.
No, it doesn't.
Oh, it still does. Okay, perfect. Okay, good. So just a few notes on the kind of patterns that we are going to look at, because every molecule, thanks to the laws of quantum mechanics, actually has its own pattern of lines. So a carbon monoxide molecule, it can both rotate and vibrate at the same time, and you get these so-called P and R branch lines that you see here in this vibrational mode. Molecule like CO2 also has a so-called Q branch, which has a delta J equals 0. So it has a slightly different pattern, and it's especially these Q branches that we can see quite readily in our data. And then you have a molecule like water, of course, a very important molecule also for astrobiological reasons, but it's a little bit of a beast in terms of its spectroscopy. There are sort of several hundreds of lines that are spread throughout the mid-infrared range. So it's a very irregular pattern, actually, that we get. Another thing that we can immediately say from our spectra is how cold or how warm it is. Because if it's warm, you start to populate more of the levels, and that means that you get not a narrow pattern, but a much broader and broader pattern. So you can just look at the spectrum and already say, hey, that's cold and that's warm. So more generally, what we do with these kind of data that we get from Webb is that we fit models to that. We call them SLAP models, in which we have actually as the main three parameters the temperature, the amount of molecules, so we call that the column density, the emitting areas, and we get a little bit of information on the velocities, but at the resolving power that we have, that is not so much. Okay, good. So let's start at this embedded stage, where we have sort of a star that is being built up. There's a young disk around it. There's material still following in, but there's also an outflow actually emerging here in a perpendicular direction, perpendicular to the disk. So this is a cartoon, but previously, previous mission, we're not able to resolve anything like this. It was basically one big plot. And now we actually have these sophisticated integral field spectrometers on Webb, in which we actually can get spectral images. So we can now actually dissect this because the spatial resolution of Webb with its 6-meter diameter dish is very well matched to these different components. So there's a whole slew of scientific questions that we can actually address with a single data set. I will not say that much about it here. I'll just give you a few highlights, but if you want read more about it, go to our website. And there's an overview paper that I published just last year. So we got these beautiful images of protostars and jets. In fact, this source here is such a young source that it's still completely obscured, even in the infrared by dust. So this is a PowerPoint dot. This is not the source itself. But you see the outflows that it has. It tries to push away its surroundings. It's basically the jets that have been launched there from the disk. So this is also what our young solar system would have looked like when the solar system was only 10,000 years old. It would have looked something like this. Now, what we've learned scientifically from these kind of images is that the jet in these very early stages is actually mostly molecular. It's not yet atomic or ionized, that is just at its core. And so we can actually now, with our spectrometer, also take images in each of these individual lines. So if you take a spectrum, you see hundreds of lines, and you can now actually make an image in each of these lines. So we see not just hydrogen, we see sulfur, we see iron, we see nickel, we see fluoride, we see all of the elements. And so this tells us also something about what the dust grains are made up of, because we see them basically being covered, these dust grains in these jets, and that tells us something about the composition of these jets. This morning we were also talking about disk winds. The evolution of the disk is certainly accompanied by also winds that carry off some of the angular momentum. And now with Webb, we are for the first time actually able to see these winds and quantify them, because we are seeing them directly here in the molecular hydrogen lines that we have. So this is the typical sort of anatomy of such a jet. This is a nice camera image that we have the edge on disk, and here is the outflow. And the jet that is in iron is actually very narrow, but then we have sort of this broader wide angle wind that is traced in the molecular hydrogen lines, and that we can now quantify directly. So if you want to know more about outflows, jets, and winds, please come and talk to me. These are some of the main conclusions that we have. First of all, that you need to have an integral field unit in order to image this. A single pixel would not be enough. We have a nested structure. We have sort of the driving agent changes from molecular to ionized, and we can also quantify these mass loss range. The other thing that we get in these embedded stages is the cold outer envelope, the ices, where it's still cold and dense, and where the molecules can freeze out on the grains. So if you look here at the beautiful MIRI image of the pillars of creation, then this is sort of a zoom of what a dust grain might actually look like, consisting of silicates and carbonated material. But you have these various molecules that can actually freeze out onto the grains and then react to form other molecules, and then form basically an icy layer on top of them. So then the question is, how do you actually recognize? How do we know that it is ice and not gas? Well, spectroscopy comes to the rescue, because actually where there are molecules in the gas or the ice, you can very nicely distinguish them. In the gas, we have this whole, set of raw vibrational lines, whereas in the ice, everything collapses into a single broad feature, which we can recognize easily. So we can study the ices both in the cold clouds, when we look towards a background star and we're looking along the line of sight, or we can look here at a protostar, and then we can look along the line of sight, both the cold ice and the warmer gaseous molecules. So this was one of the first spectra to come out, actually from my colleague, Melissa McClure, a combination of the two spectrometers, NIRSpec and MIRI. And the quality of the data was just absolutely staggering. And this was one of the first spectra that we saw. We are now looking at micro Janskis, actually, in terms of sensitivity. So at a level that, usually we're used to seeing noise at this level rather than at this. So you see here the absolute quality of this data. We see the various ices, water, CO2, CO. The silicates, of course, are here. This is the stellar continuum, out of which you see these absorptions basically happening. The lesson from this is we can now make ice inventories prior to star formation. And what it tells us also from seeing some of these features over here is that some of that complexity already starts quite early. So now we go to, from a background star, now we go to a protostar itself. So rather than having a falling continuum, we now have a rising continuum towards the mid-infrared, but we still have all of these features actually that are eaten out of the continuum by the absorption of the cold ices along the line of sight. You see the beautiful quality here of the data, in this case from Himanshu Tiaga, of an other program that's by Tom McGee's, the IP8 program, where we've actually done a lot of ice studies on. So let me just focus on a couple of features. This feature over here that is due to 13 CO2, and then I'll also focus on this other part over here where you see some weak features. I always like to focus on the weak features because that's where most of the new information are. The strong features are also good, but they usually tell a story that has already been told. Okay, so this is actually 5 sources going in luminosity. And then you see already that there's a clear difference in the profile that you see of these ices. And in comparison with a lot of laboratory data, but we also do in Leiden, you actually can see that this extra feature over here is actually due to a heated ice. The ice has been heated in which the water and the CO2 is no longer intimately mixed, but it's actually segregated into a near pure CO2 feature that you see. So this tells us immediately something about the thermal history of the ices, whether or not they have been heated or not. And that tells us then something about the chemistry. So we see these features very similarly both at 12 CO2 and 13 CO2. That also actually allows us to get a quite accurate 12C over 13C ratio, which is interesting then for comparison with the exoplanets. You know, is this preserved or not? There were some claims of very low values in exoplanets. We find actually quite high values, ISM or higher, that in these ices. So that means if you want to build exoplanet atmospheres from these ices, we are delivering ices with actually a quite high 12-13C ratio. Okay, what else do we see? Well, we actually also see some rather complex molecules in these ices. And this is one of our highlights that we had, early highlights that we had. We focused on these very weak features between 7 and 8 microns. That is a range where JWST excels compared with early emissions. And we could now see all of these weak features that in comparison with laboratory data, we could then start to assign both to CH4, a lot of CH4 ice, but also some more complex molecules. We see methanol, we see actually ethanol, we see formic acids, we see acetic acid, and we also see some salts, actually ammonium salts that are giving some of the negative ions that we also see here in this mixture. So this was actually highlighted by NASA as a press release, and of course the NASA then takes it and runs with it, and they make something out of it in the story. They called it Cheers, and then the popular press started putting alcohol and salt and vinegar, etc., together, and they came up with a margarita. And so before we knew, we were trending as margaritas. So it is also a little bit of a warning. Be careful with the wording in your press releases as to where it's Okay, salts. So salts are actually quite common, and both in our ices, but also in comets. And actually, Katie Slawizinska, PhD student in Leiden, was inspired by Katrien Altweg, who talked about the detection of ammonia hydrosulfide salt in comet 67P. And then she started thinking that, wouldn't we see that also in our own ices? And there is this well-known feature here at 6.8 microns, very strong in most sources, that has always been tentatively assigned to NH4+, but we could never make it work quantitatively in terms of the negative ions. A lot of NH4+, but not enough negative ions in order to balance it. So, what was happening here? Then she realized that actually this hydrosulfide salt gave an SH- feature that was very difficult to detect, low intrinsic band strengths, but could actually make up a lot of the sulfur in these clouds, up to 20% of the sulfur in dense clouds, compared with sort of 1% that is in say, SO2. So that was actually, she called it 2 birds with 1 stone, and that's addressing both the question of the salts, the NH4+ feature, confirming it as NH4+, and also finding a significant budget of the salts in the form of this ammonium hydrocycle set. Okay, there's another feature that caught Katie's eyes, and that was this one. It's right on the wing of the very deep 12 CO2, the green one here, 12 CO2 feature. And what is it? It's actually the deuterated version of water. So H2O ice you've seen is a booming absorption, is a very deep absorption. HDO ice, which is at as an abundance of less than 1%, is this tiny feature here of this on this wave. And so she was actually able to detect that and analyze that in a beautiful way together with the laboratory data, showing here actually how complicated this feature is with both HDO present in amorphous and crystalline form, but also methanol actually interfering here this way. She beautifully disentangled all of that. So what is the outcome in terms of the numbers? So this whole question of D/H in water has been a long-standing sort of question and tool in order to trace the origin of water on Earth. We know that the water in Earth's oceans is significantly higher than that in the sun and in the interstellar medium, about a factor of 8 higher. The question is always, is this then delivered by comets or any other icy bodies? So comets are known to be slightly higher than the meteorites in the Earth's oceans. And we are trying to trace this back to sort of a protostellar stage. Now, all of these previous data were always taken in the gas phase. And the question is this representative of what is in the ice? So Katie is now for the first time able to actually measure this in the ices. And interestingly, this number is actually very similar to what is found in the gas phase of these protostars, still somewhat higher than what is found in comets. And just the other day, what is happening? I3 Atlas published its number. It's actually surprisingly high. This is this interstellar comet. It is zooming through our solar system, probably comes from somewhere out in space. It has this very high D/H. I think what all that means is the temperature gradient, that these ices were formed at very low temperatures, 10 to 15 Kelvin, whereas the comets in our solar system probably originated in a somewhat warmer environment. There's this idea that the sun formed in a cluster and that therefore it is a somewhat higher temperature of say 20 to 25. That could explain sort of these movements that we see. So by now we have quite a number of other data, and there seems to be a quite universal HDO for water ratio that we are finding in the ices somewhere around this value. Okay, so what does this all mean? It means that we think we understand the formation of water and also how it is transported. This is a movie that we made some time ago when we were doing the laboratory and observational experiments on water, Mr. Herschel satellite. Once a day, a hydrogen atom lands on a grade, it finds another hydrogen, takes off. But it can also find an oxygen. Two oxygens can find each other and make hydrogen peroxide. And then they can further hydrogenate it to two water molecules. So what you see here is in a few days, happens in a few days on a grain. And now we fast forward to some 10,000 or 100,000 years in space. And that is how you then form these isomentals on the dust grains. So if you think about it like this, and you think that most of the water is actually originating from these cold dark clouds, as we are tracing them also in the deuterated version, then you can say, as one of my colleagues called it, that the water is actually older than the sun itself. So that's an interesting notion when you're actually taking a little sip of water. And then doing now that water is some 4.5 billion years old. Okay, so summary of the ice is very active area of research, still lots of data to be explored, but we are learning already a lot from both simple molecules, from complex molecules, solvent-bearing molecules, and also the water. All right, a little bit of the gas phase molecules, because we see them as well. So we're talking about the ices, but the closer we get to the protostar, the warmer it is, and these ices will basically sublimate into the gas phase. And we see that, this is where we see those patterns that I talked about earlier. Here is the ice band of CO2 ice, but here we see superposed actually the P, Q, and R branches of the CO2 in the gas phase. And you can just read off from this distribution that this is rather cool. CO2, it's about 150 Kelvin. We see other molecules. We've seen SO2 for the first time, CH4 very clearly, SiO actually. It's a whole story to tell about SiO, which I will not do today, but it's a whole interesting story by itself. Carbon monoxide, and of course water. So we have beautiful high signal to noise data on our protostars. Sometimes we see it in absorption if the geometry is right, that we're actually looking along the line of sight. And what I'm now going to show you is a little movie where actually the top is the data, that's the model, and the bottom is the model. And we're going to look at the similarities between them. So this is sort of the cinematic edition of the spectrum, where you can see we're now in the range of the water. In the 7 micron range, you see here the molecules that are popping up. Now we are seeing methane. You just see how well quantum mechanics works. It's just fitting all of the features that we're seeing beautifully. And then we get into acetylene here and hydrogen cyanide. And now we are getting actually into our carbon dioxide. So we can quantify all of this. This is a very clean experiment. And we can actually show that what we're seeing here is what we are calling a hot core, in which ices are basically sublimating into the gas. So that means also that we can use the gas data to tell us something about what was in the ices. Okay, good. So there's a lot to tell here as well, but this is just to show to you that there's a whole gas phase component as well to this story. All right, so for the remaining time, I'd actually like to focus on the later stages, on the planet-forming disks. And I really like this particular image of JWST here of this edge-on disk. It's a rather young disk still. You see here also this disk wind. You see galaxies in the background, galaxies everywhere. JWST is taking beautiful data, images of these disks, but most of the science is actually in the spectroscopy. Okay, so if we're looking here at the cartoon of a disk, then ALMA is very well suited in order to study the outer part of the disk. JWST is a warmer material, warmer gas, And that means it's looking more in the inner part. It's looking at the inner part where the terrestrial planets are formed, and the parts that ALMA actually cannot see. So if we look here at sort of a cartoon of our own solar system, then we know we have our sun, warm close to the sun, cold further away. So you have your rocket planetesimals, you have your icy planetesimals, and then you also have the giant planets that are outside where we think that the snow line was in our own young solar system. There has been a lot of debate as to whether that is by coincidence or whether that is actually the place where you preferentially form giant planets just behind the snow line. Now, what we are looking at is these icy grains that are coming from somewhere out in the cloud and entering the disk. But because they have a little bit of a headwind with the gas, they lose angular momentum and they can actually move inwards. And when they do so, they will actually sublimate the water and return that to the gas. But we also know from ALMA that these disks are not smooth, but that they can have these so-called dust traps that we see so beautifully in rings here in these disks. And that is where you can actually trap these dust grains. So take another dust grain, and if there's a trap maybe just around the snow line, then it actually is a big stop sign. It says, thou shalt not pass. And says, keep sort of the volatile material coming in. So what does that mean in practice? Well, if we have a disk like this, we have our icy pebbles, oxygen rich, that have moved in actually, then what we expect is an outer disk with actually a rather high carbon over oxygen ratio, but overall depleted in carbon and oxygen because most of it is actually located in the ices over here. But a little bit more oxygen than carbon is in the ices. And that is why the material that is left behind is depleted both in carbon and oxygen, but more depleted in oxygen, and therefore COO larger than unity. And this is what has been observed for quite a number of disks. For example, through the bright C2H emission. Sorry, C2H emission. So if these cross the snow line, then you of course sublimate all of this and you expect a high C over H and O over H ratio in the inner disk. Now, if you have one of these traps, where you have, say, a giant planet having one of these dust traps that locks up these pebbles, then actually you expect just the opposite. You expect a very low C over H and O over H ratio in the inner disk. So it's not only C over O that is important, it's also the absolute abundances of carbon and oxygen in the inner disk that tell us an important story. And of course, for making giant planets, that's the gas that makes these giant planets. An important question now is sort of the leakiness that you have of these traps. Is anything still passing through these gaps? Because the composition of the inner disk and the forming planets depends on where these dust traps are, when they were formed, when were they formed in the evolution of that, and also their leakiness. So this is actually what the MINDS team has been studying that you see over here. And so please see these papers for overviews of the program. We're quite far along already in the analysis. There's also another group in the US, which has a lot of time on this JWST collaboration. So if you're interested in this topic, please check out their papers as well. So quite early on, we already noticed that there was a very large diversity in the chemistry. It was hinted already at building on the Spitzer results, but of course, much clearer seen now with JWST. Here is the disk, one of the first disks that we studied with a bright CO2 feature. And when analyzing it, this is the data and the model spectrum. It first took us a few months to understand that whether all of these wiggles were real. You know, instruments have effects. You can have fringes, you can have all kinds of effects. And it took us a few months to realize that, yes, all of these features were real, and you could all ascribe them to individual lines of these molecules, common molecules, like CO2, HCN, C2H2, but also here even the 13C isotopal lock. And the detection of that 13C isotopal lock told us immediately that there was actually much more CO2 in these disks than we thought before. Now, there are other disks that are actually quite water-rich. In fact, most of the Titori disks are actually quite water-rich. And you see that here in this particular disk. This is work from Leiden and Leiden Kasman. And what you see here, this is not noise. All of this is water lines, just full of water lines. We can characterize them as hot water lines, warm water lines, and cold water lines. Mostly going actually with wavelength. And if we analyze that then quantitatively, then we find actually that the temperatures go from some 1000 Kelvin down to just above the snow line at 200 Kelvin. Now, interesting, of course, Peter has developed beautiful models in the Prodemo collaborations of water in disks. And I always like to go back to this 2009 paper because yeah, it's already there. That's where the bit differentiation comes from. And that is now exactly, there has been a whole slew of other models since that time, but this was sort of a pioneering paper in characterizing the water reservoirs in disks. That is exactly actually what we now find here, and we can now quantitatively test these disk models also in the temperature. And that is, for example, what Marissa Frasboom has done and shown that these models are actually very close in terms of the temperature structure and also in their abundance structure. What we get from these analysis of the data is now actually an indication of where the emission is. So look at this. We enter 1 astronomical unit. So with ALMA, we're looking at 20, 30, 40 astronomical units. Now we're looking very close, the inner part, Earth radius in these disks. We see the water, we see HCN, C2H2, CO2, and we can, based on their temperatures and emitting areas, we can sort of locate them where they are in the disk. One of the big questions is, well, do we actually see this effect of these drifting icy pebbles coming in and supplementing this water at the snow line? Because that would, of course, enhance enormously the oxygen in the gas. And the question is, yes, but, yes, but, because we don't see it in all of the disks. Milou did a survey of sources where in all cases we expected to see this enhancement of water. And out of the 8 disks that she studied, it was clear only in 2 of the 8 disks. So how are we analyzing this? This is from the JWST collaboration. They actually, Andrea Lanzatti, developed this sort of diagnostic plot of cold over warm water versus warm over hot water. And the ones that are enhanced in cold water should be over here in this diagram. Interestingly, most of the MIND sample and also the JWST sample is in this part of the plot. It's not much enhanced. Only a few of them have this very clear enhancement. So that is a little bit of a puzzle as to why we are not seeing that. And so both Andrea Lanzatti and also Marissa Frasboom have looked at another set of lines. This is just a quartet of lines that one can look at around 23 microns that are particularly diagnostic of the cold water. If you see an asymmetric pattern, that's a lot of cold water. If you see a symmetric pattern, all of these 4 lines equally strong, that's warm water. And so we've been trying to understand that. And Marissa, this is now a little bit more detailed for the experts in the audience, actually showed that what sort of Peter's model would give and also our models would give is indeed emission here from this layer, but not as far out beyond the snow line. And what the data actually require is much more water somewhat further out, higher up in the layers. And we cannot get that with any of our chemical models because water is photodissociated so quickly. So you need to replace, you need to actually replenish it much more quickly than is happening at the moment. So what we think is actually happening here, and that's sort of work in progress, that we're actually delivering a lot of water here at the snow line, but somehow it's also mixed up very efficiently to these upper layers where you can actually see it as this cold water. So the main message is that, you know, these cold water lines have a really good diagnostic of the water delivery at the snow line, and we're trying to quantify them in more detail. So we see water in some cases. We've seen also have some CO2. So some of the disks have some water but are more CO2 rich. Here's a water rich disk. Here's a CO2 rich disk. This looks like one of these drift dominated models with enhanced water delivery. This one, the only way we can get rid of the water is actually to think that there is a small cavity actually in the inner disk. That is basically suppressing the water. On the other hand, so far we have not yet found a clear relation with the dust traps in the outer disk. We are now getting new ALMA data in order to test that. There's another possible explanation, and that is actually sort of a time sequence. So if you have sort of a disk, you have the water snow line, you have the CO2 snow line, a little bit more volatile, you have the CO snow line. So the water-rich grains will come in first, they drift in first. You get this enormous delivery in water, but the CO2 comes in a little bit late. So maybe that is what is happening here, that we are seeing the CO2 coming in later. There's a little snack here that was noticed by both Andrew Selleck and also Hauge here. You bring in not only water, but of course this water is on the dust grain. So you bring in also dust. And once you bring in dust, you obscure your emissions. So it's nice, you bring in the water, but maybe you're not seeing it. And the Hauge et al. Paper had a nice title, Smuggling Unnoticed. Smuggling in the water, but it remains unnoticed. So very good catchy phrase. So this is something to take account, and we are still struggling on how to address this, whether or not we're seeing the water. One way we're doing that is we're now actually looking at the younger disks, at the class 1 disks, the embedded disks, where we just have our data delivered from a follow-up program, and that we are analyzing, and that we can sort of address whether it's especially these younger disks that have a lot of water and that's delivered. How about these cavities and the leakiness? Well, there's one beautiful disk here, PDS-70, which is well known because it has these two giant planets in it. The only disk, well, now there's a second one, but until recently, the only disk that we knew that had two young planets already in it. And what we thought was that all the water ice should be trapped over here and that we would see nothing over here. But yet, actually this MIRI see a very nice water spectrum coming here from the inner disk. So this is where the MIRI spectrum is coming. So clearly these very deep cavities into these two giant planets that are forming there are not completely empty. There is material passing through it and getting to the inner disk that you see here. Not much. If you would quantify it, it would be about your sea of water that is getting there, but there's still some of it. So we have this emerging diversity. This is in the same cloud, the Taurus molecular cloud. This is BP tau, very bright in water lines. Another source, CY tau, that is bright in C2H2. And you have a third source that is very bright in C. So we're now trying to understand this diversity just in terms of the Titori stars. So this is work by staff doing, but building, of course, on a lot of other work that is looking at the hydrocarbon networks like Walsh et al. And Jayati Kanwar, here also in collaboration here in Graz, and Aditya Adabavi. Interestingly, we can sort of explain the observed diversity with a varying C over O ratio, but always still less than unity in order to explain this. Okay, good. The final few minutes of the talk. I'll try to turn to these very low mass stars. And so far we've talked about the sun-like stars and half a solar mass. Now we're going to the very low mass stars and the brown dwarfs that are less than 20% of the mass of the sun. And these were the surprises actually, because they turn out to be surprisingly rich in hydrocarbons and almost no water seen, or any water is basically hidden by the hydrocarbon lines. So what we get here is now orders of magnitude higher acetylene than for the Tittori disks, and even benzene is detected on these disks. No silicate emission. We may actually be looking very deep into these disks. This is work by Raymond that was. And this is not the only one. Virtually all of the very low mass stars and brown dwarfs, and by now we've looked at some 24, are very rich in these hydrocarbons. And they even have a forest of lines. So this is not a continuum. This is not a silicate dust emission. This is really thousands, maybe hundreds of thousands of lines of acetylene that are contributing to this single feature. And we see the isotopologues. Here we see nicely these Q branches, benzene, we see CO2, we see, what is it, HC3N. There's the isotopologue again. We see the HC3N. So all of these molecules, here is diacetylene. They are full of lines. They are actually waving us at us and showing that. So by now also the line lists become incomplete. So I know you exoplanet people have lots of lines to deal with, but we have now as well. So hydrocarbons can be abundant and also diverse. Here you see. So how common are they? Well, in fact, it's quite common in the sense that if you look at here the luminosity or the stellar mass, and here you look at the flux of acetylene over water, then the Tittori stars are over here, and the very low mass stars, and now also the brown dwarfs. We have another dozen of dwarfs that they are all actually over here in this area. There's a little bit of overlap, so there are definitely a couple of exceptions to this rule, but by far the bulk of them are sort of in these two categories. So for this, we need a carbon over oxygen ratio greater than unity. For this, we can still explain it with less than unity. So what then explains this dichotomy? How do we get C over O less than greater than? So what you can do is you can either enhance carbon or deplete oxygen, or do both, because both will help to raise your C over O. How do you deplete oxygen? You lock it up in icy grains. How do you enhance carbon? Well, this is an idea that has been around for quite some time, actually, in the literature. We know that 50% of the carbon is in grains. So, what if you cross what is called the soot line? Maybe not very good wording, but sort of indicates what is happening. That you release that extra 50% of the carbon, and you basically push your carbon over oxygen just above unity. Once you're above unity, then you very easily create all of your hydrocarbons. Now, if you remove your grains, and so if you sublimate your grains, perforce them, and you get that into the gas, that gas is removed, so basically that is removed. Then what kind of planets do you make? You're not going to make carbon-rich planets, just the opposite. You're going to make very poor, carbon-poor planets. And that's actually the idea what happened to the early Earth. We know that comets are very rich in carbon, but the Earth is very poor at carbon. It's down by 3 orders of magnitude or more. So what we end up with then in these disks is a gas that is very rich in carbon. And so if you're making your giant planets, there you have these meridional flows that sort of make the atmospheres of these planets, then you would actually make a high carbon over oxygen planet. Okay, there's another scenario, and that is basically, that's also popular, and that is sort of this drift story that I've been telling you about, taking into account the fact that in these very low mass stars, because the mass of the star is so much lower, the drift is actually faster, and that means that after you've brought in your water and you've brought in your CO2, then the next snow line that you have is the CH4. So you bring in a lot of CH4 faster. So if you look at a solar mass star, this is actually the time, and this is radius. So focus only on this part. This part is blue, with low C/O. In a solar mass star, and even half a solar mass star, it takes 10 million years before you reach sort of when the carbon-rich materials being brought in. If you go to these very low mass stars, you see that this carbon-rich material is already being brought in much earlier. And so that is also an alternative popular model that would happen. It's not without its problems as well. And one of the problems is actually that you can get to a C/O ratio close to unity, but it's not that easy to go over unity. Yeah, so these are the solar mass stars, the very low mass stars. So that is why with Andrew Selleck, we've been looking at ways of really getting above this C/O is unity. And the only way to do that is to also have energetic radiation to break the carbon monoxide. So in the early stages, you bring in a lot of oxygen, so you have a very low C/O ratio. Then you get to the carbon-rich phase, but it's very difficult to cross this line unless you also break the carbon monoxide and advance that carbon-rich gas. Good. So I was about to stop here indeed. The next step is to go even to the smaller, to the circumplanetary disks. And there are now a couple of very exciting results there of looking at a disk, a moon-forming disk around a Jupiter-like planet. And so she also turned out to be full of these hydrocarbons. So they are also hydrocarbon rich. So this, whatever is this process is, it's continuing down into the moon-forming regime. Just to summarize, this chemistry is diverse, and the main drivers are the radial drift, the trapping of dust, the destruction of the carbon-rich dust. The dust growth and settling, looking deeper into the disk, is definitely also an effect. All right, I'll leave it here and hope to have given you a taste of what JWST is telling us. Thank you very much.
Thank you very much for this enlightening talk. Do we have questions? Young people feel encouraged to go first, maybe? While you're still thinking about your question.
Very nice talk. I love this. I have also probably, you're uploading it, right?
Eventually I will, yes. It's going to be recorded. And,
yeah, because I would like to go back to this. It's very nice. The H2O ice. I'm wondering how you actually can detect those. So does it mean that the ice layer is very thin? Because if you have like 1% of H2O and you form ices, how do you circumvent being buried by the H2O ice, right? I mean,
it's not yet optically thick, as we would call it. So you form at most 100 monolayers on an ice. If you use all of it, well, as a surface science physicist, you call it a thick ice because surface scientists like to look at monolayers. But if you lose all of your oxygen on a 0.1 micron size grain, then you have about 100 million monolayers. But still, you can still look through that.
Okay, cool.
Thank you. Yeah, I agree. That was a very, very cool talk. I have a question about something that I haven't really thought about before, but when you talked about these first results on the carbon abundance in circumplanetary disks, How does that compare with the composition of the solar system moons? Like if we look at Jupiter, would you infer from this that Jupiter was like CT-KB?
Well, very good question. That's indeed something that we're trying to understand now. I don't know the answer to this, so I think I've asked the same question at some stage since I'm not involved in these studies myself, but except, sitting around a table and somebody showing at one of the MIRI team meetings, showing us the spectrum of the circumplanetary disks and not knowing what these features were. I said, oh, that's all of your hydrocarbons that you have there. But yeah, it's fascinating to think about that. I don't think that they are hydrocarbon rich. So again, we now have it in the gas phase, so it can actually flow away. That's substantial.
Hi, thanks for the nice talk. I have a question because if stars are young, their luminosity is also evolving with time. Would you expect that to affect the C2 ratios?
Yeah. So, I mean, this is something that is taken into account in some of the models, not necessarily in all. So indeed, if you look at sort of Titori stars and certainly the very low mass stars, the M dwarfs are of course very active. And they have lots of flares and whatever else. So, whereas the Titori stars may have these Titoriospheres in which you exclude the cosmic rays that could destroy the carbon monoxide. So there's definitely things that happen with time and that are also different than in time between the Titori stars and the very low mass stars. That one could take into account, and that may sort of have I would not say zeroth order effect, but first order or second order effects on these all these stories.
Questions?
Thanks for the talk. I just have a short question. Maybe I missed it, but what's the reason why low-mass stars have a low C2O ratio? You had the model.
A high C2O ratio, so
Yes, here,
this one?
Oh, high C2O, sorry.
Yeah.
So what is
Yeah, so that's basically the CH4 that is being brought in much earlier than in the Titori stars. So you would get the same pattern in the higher mass stars, but at a later time. So you see it just happening, over here. Here's where you start to go from blue to red. So basically from low to up to high. So all of this, if you first bring in the water and then you bring in the CO2, both of them are oxygen rich. So you go very dark blue originally because you bring in a lot of oxygen. And then you start bringing in carbon and then you switch to carbon rich. And that happens sooner for the very low mass stars than it happens for the high mass stars.
Okay, thanks.
Question, so maybe.
Thank you so much for this wonderful talk. I think I could listen to this again and again. So it's very inspiring. I think I have various questions, but let's start with a potentially simple one. You said that in disks you see when the ice has been reheated because you then suddenly see two distinct species.
Yes.
Exactly. So would you expect the same thing to happen for solid materials?
So this is in the ICES, it's happening. Yes, it's so in terms of, we see that already happening in what we see in the solid materials, we see the crystalline that is happening also already in the disks. We know that from in the interstellar medium, the silicates are mostly amorphous. By the time we get to the disk phase, it's typically of the order of sort of 20% silicates, crystalline silicates. Yeah, and we saw that already with Spitzer. We now see it always growing until with Webb. That is a very nice paper by Joseph Varga that has just been submitted on the mines sample. And we see even silica, not just the silica.
A naive question, why do you see the separate ice phases at all? Because if they recondense, they should basically, if they move from outward inward, then they should condense almost simultaneously.
Yeah, so we think that actually certainly the water is formed on the grains. So it's not, we don't think that a lot of, we think that most of that is preserved and not necessarily recondensed. So carbon monoxide will definitely, because it's so volatile, it will sublimate and recondense and sublimate and recondense. But the stronger bound molecules that are sort of bound inside the water ice will sort of not be processed, as we call that. Yeah.
Someone else wants to.
Maybe last question. I wonder, you have pointed this instrument to all kinds of objects and also to classical class 2 disks, but I haven't heard yet about the ice detections in class 2 disks. Do you know? Are there some findings?
Yeah. So there's a whole active group there, and we have some of it in mines as well that is looking at this. So, in fact, that is mostly Melissa McClure, who's her team. Sorry, shouldn't have done it. I wanted to get to basically this case. Yes, so this is a beautiful edge on disk. But you can point at them. So mostly you would see the ISIS because the ISIS go in emission only in the peripheral. That's why we need a new fluorescent emission. But you can try to see them in absorption if your disk is edge on, and then you would have the scattered light basically going through there.
No, I was asking because in the end, if you would have a disk model where you allow disks to be coming up fairly high in your model, you would see actually the ice features right away. We don't see it normally, only in this particular geometry. We might have a chance to get this ice in the way of a warmer background, and then we see it. But I think this is actually a nice confirmation, or still, I think it's worth looking into this. How much up do you get the ice? Because if you would, then you would see it. We don't see it regularly. So that means you have some constraints about the chemistry and the
Yeah, exactly. And that's what Sturm et al. Did in the HH48 paper. And now there's a new paper just a few weeks ago by Jenny Birkin, sample of edge-on disks. In all of these cases, they see the CO higher up in the disk than you would expect based on its volatility. So it must be trapped in the water ice in order to get it up as high in the disk atmosphere as you get here. But these kind of data are very hard to interpret quantitatively because the photon takes a tortuous route from the star through the disk out into that. So they are very hard to interpret these kind of